Right, so for gravimetric analysis, it can take two forms depending on what we're trying to analyze. So for example, if you want to analyze the moisture content of soils or even salt, so like copper sulfate that contains, sorry, how you fix? I keep talking, but nobody hear me. I'm not sure. Nothing.
Yes, we're hearing you.
No, someone says she's talking, but we're not hearing her.
She has to her own audio because I'm hearing you.
All right. Right. So, for example, compounds like copper sulfate, they might have been a certain number of moles of water, which we call water of crystallization. So we can use gravimetric analysis to figure out the number of moles of water present in a sample. All right. So with this form, if we're doing gravimetric analysis to basically determine the water of crystallization, all we would do is wait. Somebody's mic is on. Just remember to mute your mic. All right. So if you have a sample that contains water, and you want to figure out the number of moles of water present, we will just record the mass of the salt first. Now, when the water of crystallization is present, we say that the salt is hydrated. Right? So this would be your hydrated sample of copper sulfate. What we would do is record a mass for the copper sulfate. So let us say you go in the lab, right? You get a container, and let's say you measure out 5 grams, or you could just take up a spatula full of the copper sulfate. And so what you would do, you would weigh your empty beaker, right, or crucible, whichever container. So you would weigh the mass of the empty container. Right? Let's use crucible. Right? Just a second, let me mute this person. Right, so you would record a mass for the empty crucible. And then you would place a sample of the copper sulfate in the crucible. And you would record the mass of it as well. So you would have mass of empty crucible. And let us say the mass of the empty crucible is 24.5 grams. And when you add the copper sulfate sample and weigh it again, right. Class students, remember to mute the mics. So we have the mass of the empty crucible. We place a sample of the copper sulfate in the empty crucible and weigh it again. Now, you must also know this procedure. All right. So basically, I'm going through the procedure. So two ways in which we do gravimetric analysis. I'm showing you the first one, which is basically to determine the water content of a salt. You can do it for soil samples as well, but the procedure is the same, right? You weigh an empty container, you place a sample in the container, and you weigh it again. So let us say now the crucible with the salt is equal to 27, let's say 28 grams. All right, that is what you would do. And then now, after you do the weighing, you are going to heat this sample. So you can do it over a Bunsen burner in the oven, but you will heat the sample until all of the water has been evaporated. If you want to be sure that all of the water has been evaporated, you are going to heat it for a certain amount of time, allow it to cool, then you heat it again. And once you see that the mass remains constant, then you know that all of the water has been evaporated. So you will heat it until the mass becomes constant. So you heat, allow to cool, heat again, allow to cool. Once you see when you keep weighing it and the mass becomes constant, someone's mic is on. Right, so once the mass becomes constant, then you make a note of the weight. Sorry. So remember, before it is heated, the salt, it will be the hydrated salt because it contains water. Now, after you heat it, it will be the mass of the crucible with the anhydrous salt. So when water is present, it is hydrated. When no water is there, it is anhydrous. So let us say after we heat it, it's at the mass of 26.4 grams. That's the experiment, right? You have the mass of the empty crucible, the mass of the crucible with their hydrated salt. Then you're going to heat it so that all of the water can be evaporated. Then you record the mass of the salt after heating, all right? And that will be the anhydrous salt. So this is the salt before heating and after it is heated. So in terms of calculations, the first calculation that we need to do is to get the actual mass of the hydrated salt. Because if you'll notice, we did not say we're going to weigh 2 grams or 3 grams. We just put an amount in the crucible and we weigh it. So we have the mass of the empty crucible, we have the mass of the crucible with the hydrated salt. So to get the mass of the hydrated salt, so if the mass of the crucible with the hydrated salt minus the mass of the empty crucible. So that would be 28 minus 24.5. That should be 3.5 grams. So this is how you would work out the mass of the hydrated salt. The mass of the crucible with the hydrated salt minus the mass of the empty crucible. Now on the exam, they don't have to say mass of crucible with hydrated salt. They can say mass of the crucible before heating, right? So mass of the crucible and the salt before heating, and mass of crucible and salt after heating. All right. So after that, we're going to calculate the mass of the anhydrous salt, which is the mass after it was heated. So it's the same thing now. It's the mass of the crucible with the anhydrous salt minus the mass of the empty crucible. And that would be 28 minus 26.4. And that should be 1.6 grams. Right, so mass of empty crucible, crucible plus the anhydrous salt minus mass of empty crucible, you get the 1.6 grams. Once you get the mass of the anhydrous salt and the hydrated salt, no, not from a document. This is just an example I'm making up. All right.
Sir, wasn't the empty crucible 24.5?
It was 20, right? Oh, thank you.
It's the hair.
Yes, sorry for that. Thanks. I'm hearing you. So the empty crucible was 24.5. So that should be 0.9. Not 0.9. Let's do that. $1.9. So the mass of the anhydrous salt is 1.9. So once you have the mass of the anhydrous salt and the mass of the hydrated salt, we're going to calculate the mass of water that was lost. So to get the mass of the water, it's the hydrated salt minus the anhydrous salt. So the mass of the hydrated salt was 3.5. And the mass of the anhydrous one was 1.9. 1.6 grams. So the first three calculations that you will find out is the mass of the anhydrous salt, the mass of the hydrated salt, And then we use that now to calculate the mass of the water loss. Is anybody still writing? But I'm going to erase and go to the next step in the calculation.
You can continue, sir.
All right. Just change. Roman law. All right, so once you get the mass of the anhydrous salt, which was copper sulfate, you're going to do this. So you will have copper sulfate and water. We're going to calculate the moles of each of them. So for copper sulfate, someone's mic is on. So for copper sulfate, we have 1. Right, so for copper sulfate, the mass is 1.9 grams. And for water, the mass is 1.6 grams. The molar mass for water is 18. If I remember correctly, I think they're supposed to be 160, but let us check. So copper is 64, plus 32, plus 64, 160. All right. So we're going to calculate the moles of copper sulfate and the moles of water. So 1.9 divided by, yes?
Could you remind me how you got the 1.9 again?
The 1.9, we subtracted the mass of, what was it again? The mass of the salt after heating. So it was the mass of the salt after heating minus the mass of the empty crucible. But remember, it's two forms of the salt. When it has in water, which is the hydrated, and after heating, which is the anhydrous one. So this mass here is for the anhydrous, which is the mass of the crucible with the salt after we heated it. And we subtract the empty crucible from that mass. So the empty crucible was 24.5 grams. And we said the after heating, it was 26.4. So that's the we end up with the 1.9. All right, I'm gonna get 0.0119 moles. And 1.6 divided by 18, we get 0.0889. So once you get the moles of each of them, we're going to compare and divide on. Give me a second. 1.6 divided by 18 and 1.9 divided by 160. All right, I'm going to switch. So when you do the calculation, the number of moles of water, it must always be smaller than this one. But I was just making up some numbers during the example. So this, it cannot work because this number is bigger than this one. So I'm just going to switch the numbers at this point to ensure that this one is smaller. So I'm going to change the 1.9 to 3.5 and see if that works. So 3.5 divided by 160, 0.02. No. Right, let me change the mass of the water. I'm actually correct. Sorry about that. What was your available? 1.6? Sorry.
Yeah.
Sure.
This must be the bigger number. Sorry. So it is correct. So 0.0119, you'll get 1, and then you'll divide by 0.0119. So 0.0889 divided by 0.0119. I'll get 7. All right. So based on our calculation, the number of moles of water present in our sample would be 7. So the formula, it would be CuSO4. So in the question, they would like give you the formula CuSO4 dot XH2O. And you would have to figure out what X is. So at this point, X is the number of moles of water. So at this point, you would say that the formula is CuSO4 dot 7H2O. All right? And that would be your calculation. So all of this calculation was just to determine the number of moles of water that is present.
Excuse me, sir.
Go ahead.
For the calculation underneath water, do you get 7.5?
Yes.
Oh,
7.5. Yeah.
Oh, okay. You didn't round anything?
Repeat.
You didn't round up or anything?
7.4, 7.47.
Oh, okay.
Yeah. But because this was just an example, making up, right? I just wrote the 7, but it's 7.49, so it would be 7. All right. Now I'm going to give you an actual past paper. It's just like this example that I did on the board. So all you need to do is follow the steps, and you should get it right. So just remember, we add the mass of the empty container. Then we put the hydrated sample in the container and weigh it. Then we heated the container until all of the water evaporated. Then we recorded the mass again. To get this mass here, this is the mass of the anhydrous salt, meaning all of the water has evaporated. And to get this mass, it's the mass of the container with the salt after it was heated, minus the mass of the empty container. To get the mass of water, you would have subtracted the mass of the hydrated sample with the mass of the anhydrous sample from the hydrated sample. That is how you get the mass of water. Then you come here and you calculate the number of moles. When you get both of the answers, this one is always going to be the smaller one. And you divide by the smaller number. And the answer you get here, that is the number of moles of water that is present. Okay. So I'm going to put the past paper on the board now. This one is from 2014.
Why you start show so now? What the hell?
All right, so I'm going to give you about 4 minutes or so, and you attempt it on your own.
What possible of washing soda after heat settlement? So mass of the crucible.
Someone's mic is on.
Mass of it. How much it did heat too.
Mr. Hare,
Yeah.
did they give the molecular mass of the Na2SO4?
All right. So the mass of sodium. Sodium is 23, oxygen is 16, and sulfur is 32. Any answers as yet?
Sir, I got 10, sir.
All right. I'll give the others 2 more minutes and then we'll work. Yes.
Yes, sir.
But 10 is the answer. All right, I'm going to work it now. So we are tasked with finding the value of x and formula. And the 2SO4 dot x H2. So based on the data that was given, what are some of the things that we need to calculate in order to find x based on the data?
Sir, we need the mass of the crucible.
All right, we have the mass of the crucible. So, and then what are we going to use the mass of the crucible to help us calculate?
Mass of the hydrated.
The actual mass of the washing soda.
All right, the hydrated and the anhydrous form.
Anhydrous salt.
Right. So the hydrated salt, it would be what? What would be its structure?
Sir, na be the mass of the crucible after eating minus the mass of the crucible and washing soda.
No, for the hydrated one. So remember
That would
the,
be 40.69.
right?
Minus 34.25.
Minus 34.25. And what's the answer?
Which gives you 6.44.
6.49.
All right. 6.4?
Sir, I'm get 6.44
6.44 grams, sir. 44.
grams.
Right, so the hydrated one is just the mass of the crucible and the washing soda minus the empty crucible. Now, what would be the anhydrous one?
The 37.09 minus 34.25.
What's the answer?
2.84 grams.
2.84?
Yes, sir.
Yes, sir.
And what do we calculate after this?
the mass of water lost.
All right. And that would be equal to,
Hydrate minus anhydrate.
right, so 6.44 minus 2.84, and we get how much?
3.6.
All right, 3.6 grams. All right, so we have three masses here. All right, which two
Sir?
are we? Yes?
To find the mass of water loss, sir, could you have used like the mass of the crucible after eating minus the mass of the crucible and washing soda,
Mass of the crucible after heating.
and the mass of crucible and washing soda?
Right, so mass of the crucible and the washing soda after eating.
So, sir, it'd be 40.69 minus 37.09
40.69
minus 37.09, and I got 3.6 grams.
I got 3.69.
Grams, sir. 3.6 grams.
So you need mass of the hydrated salt
Yes,
with the
sir.
crucible
Yes,
minus the mass of the anhydrous salt.
yes, sir.
That's kind of a shortcut.
Well, it works, so yeah. But I think in terms of marks, like how they set it up, but I mean, it works, so you can use it.
Okay.
Yeah. All right, so of the three masses here, which two are we going to proceed with?
2.84 and 3.6.
So the anhydrous salt and the mass of water lost. All right, so that was 2.84 and 3.6. What's the molar mass for sodium sulfate?
142, sir.
142.
And
It's 3.6.
18, sir. 18 for water.
yeah.
18.
What's the answer here?
0.02.
0.02.
And here,
0.2.
0.2.
0.2.
Yes, sir.
Yes, sir.
And so we divide by the smaller one,
Smallest.
we get 1.
And get 10.
And so the formula is Na2SO4 dot 10H2O. Right? X is 10. And so this is how this type of calculation will come. No, they can make it simpler where they just tell you directly that the mass of the anhydrous salt is 2.84 and the mass of water loss is 3.6. And you just go ahead and calculate. Or they can tell you the mass of the hydrated salt and the mass of the anhydrous salt. And you just subtract the two to get the mass of water. So it's not all the while they will give you mass of crucible and all of that stuff. They can skip out that information and just tell you directly the mass of the anhydrous and the hydrated salt. All right. So remember we said we're doing two types of gravimetry. This was one of them where you determine the number of moles of water present in a salt. The next one now is where we analyze a sample for a specific analyte. So for example, if you have a water sample and you want to find out if lead is present or the quantity of lead, the quantity of chloride ion, the percentage of calcium carbonate in a sample, let's say of eggshell or limestone, right? Stuff like that. So how does that procedure work? So let us look at the procedure. Tamika Campbell, mute your mic. It's not muted. Tamika Campbell, mute your mic. It's not muted.
Everybody.
All right, so let us look at the procedure now for the second gravimetry. So the example I'm going to use, let's say we have a water sample and we want to determine the quantity of chloride ions present or the concentration. The first thing you're going to need to do, right? So if you have a solution, right? Not a solution, you have a water sample, right? And chloride ion is present in it, and you are trying to figure out the quantity of chloride ion present. The first thing we need to do in gravimetric analysis, we need to convert whatever ion is present to a precipitate, right? So if the chloride ion is present, we need to add a solution to the water sample that when you add it, one of the ions will combine with the chloride ion to form a precipitate, a compound that is insoluble in water. Now for group 7 elements, the chloride, chlorine, bromine, fluorine, those ions, the two compounds that they form that are insoluble is with lead and silver, right? So the first thing I need to do is add a solution to your sample that will convert your analyte. The analyte is the ion that you're interested in. So what I will do, the sample with the chloride ions present, I am going to mix it with a sample of silver nitrate, right? So I have my water sample with chloride ions present. I'm going to mix it with my solution of silver nitrate. And the reason why I'm choosing silver nitrate, this is what is going to happen when I mix the two. So silver nitrate here, once it's a solution, even though I am writing AgNO3, in this solution, you will have silver ions, right, which is Ag plus, and the nitrate ion. So when in solution, these ions are not combined, as you are seeing here, AgNO3. When they're in solution, they are separated. So the silver ions is separated from the nitrate ion. So what is going to happen? The silver ions will combine with the chloride ions in the water sample. And you will get a precipitate of silver chloride. Somebody's mic is on, check your mic.
Is that Abby? Don't say mom.
Judge. Okay. Right, so the silver ion will combine with your chloride ion to form silver chloride. The silver nitrate, it is referred to as the precipitated the precipitating reagent. So when you add this solution to your sample, it will form a precipitate with the analyte. So whatever ion you're interested in, when you add your precipitating reagent to it, a precipitate should form. All right? So for next example, if it was lead ion, that is your analyte. Right? If it was lead ion, that is your analyte, when you need to add a precipitated reagent, that's when it combines with lead ion, it can give you a precipitate with lead. So for example, if I chose potassium nitrate as my precipitating reagent, when I mix the two solutions, somebody's mic is on, check your mic. When I mix the two solutions, right, the nitrate ion, which is the negative ion, that would react with my lead ion, right? But would we get a precipitate? Does anybody know? If we react lead ions with nitrate ions, would we get a precipitate?
No, sir.
No.
No, sir.
No.
All nitrates are soluble.
That is correct. All nitrates are soluble. So we could not use potassium nitrate. You could use the group 1 metal with something from group 7. Because remember we said that the chloride.
So you can use potassium chloride?
Right, because silver and lead, those two positive ions form an insoluble salt with the group 7 ions. So you could use potassium chloride, bromide, or iodide. Now, when you add potassium chloride to the solution with lead, lead ions combine with chloride ions to give you your precipitate of lead chloride.
Oh.
So the first thing in this form of gravimetric analysis, right, we're going to add a precipitating reagent to our solution. When you add the precipitating reagent, you are going to get a precipitate being formed. So this is what will happen. You have your sample, you have your precipitating reagent. Mix the two of them. And once you mix the two of them, you will see precipitate appear. Right? So you go from no precipitate to a precipitate. Now, remember we said that the precipitate would have contained your analyte, your ion of interest. Now, how would we get the solid? How would we separate the solid component from the liquid component?
Heating, sir?
Please repeat.
Heating?
Heating.
Heating, sir. Heat.
Filtration.
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 Right, filtration. So the first step, we are going to add our precipitating reagent so that we can get the precipitate with our analyte. Once we get the precipitate, we are going to filter. Now it's gravimetric analysis. So for filtration, we use specific apparatus than what we are used to for filtration. So it's not the conical flask and the separating and the filter funnel. Which type of funnel would we use in gravimetric analysis?
Butner funnel.
No.
Buckner funnel.
So let's just list them. I'm going to erase the equation. I'm going to write it back at the end when we're doing the calculation. So the first step was precipitation. right? And then we will do filtration. And in filtration, we said we are going to use Buckner funnel. What else?
Filter paper.
Filter paper.
Suction flask.
All right. And one more.
Vacuum pump.
Correct. Vacuum pump. All right. So in gravimetric analysis, for the filtration process, we're going to use the Buckner funnel, right? I know it is like this, but it has little pores inside of it. Mhm. Good. And you rest the filter paper flat inside of it, right? With the suction flask, with the thing to connect the vacuum pump to. Right? So for filtration, we use the Buckner funnel, suction flask, filter paper, vacuum pump. Now, after filtration is completed, what would you do? So inside the Buckner funnel, we would have the precipitate, right? At the precipitation, sorry, at the filtration step, what precaution would you take for filtration? There's a major precaution. Anybody? What would you do to the precipitate before you heat it?
Rinse it with water, distilled water.
Rinse it with
So
water.
rinse with water.
And why are we rinsing it with water?
Sorry, to purify it.
Right. And on the exam, don't just put water. What type of water?
Distilled water.
Distilled.
Distilled water, right? That is correct. So after you filter, we would wash the precipitate with distilled water to remove any impurities. Once we are finished with that process, what are we going to do with the precipitate?
Right.
Right. Right. So step
Right,
three.
sir.
Right. So step 3. Let me just place the other 2 steps here. So step 3, we would dry the precipitate, and step 4, we would final step.
Wait a month.
Wait.
So step 1, we obtain the precipitate. Step 2, we filter the precipitate. In filtration, we're also going to wash it to remove impurities. And then we dry it, and finally, we weigh it. Now, after you weigh it, we're going to perform some calculations. So for this procedure, also know this procedure for the exam, they can ask you for the procedure. So the major steps, well, the only step really, precipitation, filtration, drying, and weighing.
Excuse me.
Go ahead.
Did you already go through titration this evening?
No, we started with gravimetry. After this, we move on to titration, then accuracy.
So repeat. You can repeat what I just said about precipitation, filtration.
All right, so these are the steps for the procedure of gravimetry. For precipitation, we have to first form a precipitate. So with this one, right, we are trying to figure out something about a compound, like a particular component. So if it was a water sample, we would like to probably know the concentration of chloride ion or lead. So if we're doing that, we need to convert the ions present to a solid form. We need to convert it to a precipitate. So the first step is to convert it to a precipitate. So that is precipitation. And to do that, we add what we call a precipitating reagent. It is simply this solution that you add to the sample to get the precipitate. Once you get the precipitate, you filter using the Buckler funnel, filter paper, suction flask, and vacuum pump. You rinse it, you rinse the residue to remove impurities. Then you will dry it and we weigh. Then we perform calculations. So this is the procedure, you should know it. Were you asking a question? All right, so this is the procedure. Now I'm going to put some numbers on the board to do a calculation. All right, so this would be the procedure. Now let us say that the sample we're using, the water sample, we're using 25 mils of it. All right, is anybody writing? I can erase the board now.
Yes, sir.
All right. So for the, let us say, we have 25 mil of water sample. Oh, just to mention, your precipitating reagent, you always add it in excess. Can anybody tell me why we need to add the precipitating reagent in excess?
So essentially everything is dissolved. You don't have any leftovers.
So that everything is what? Repeat that part. Everything is?
He said dissolved, sir.
Dissolved.
No, dissolved is not the, no, not dissolved.
Is it to ensure that all the chlorine is reacted?
That is correct. So you want to ensure that all your analyte has reacted. So whatever amount of chloride ion is present, you want to ensure that all of it is converted to the precipitate. What happens if not? How would it affect your data? How would it affect the results? If not all of, so you're trying to figure out the concentration of chloride ion in the water sample. If all of the chloride ions were not converted in the precipitate, what would happen? Or how would that affect the accuracy of the results?
So it would affect the mole first, and then using them would affect the concentration.
That is correct. How would it affect it? Would it be higher or lower?
Lower.
That is correct. So let us just use this example, right? We have 4 chloride ions on the board. Let us say we add our precipitated reagent and only 2 of them were converted to a precipitate. That means more chloride ion would have been in our solution. And so when we do our calculation, it would not be accurate. We would get a lower concentration of chloride ions than is actually present. So that is why it is important to add the precipitating reagent in excess so that all of the ions are converted to the precipitate. Second thing, in the drying process, what would happen if we did not dry it properly?
It would be higher.
It would affect the mass.
Yes.
And if it affects the mass, it would also affect the
concentration.
Right. Now,
the mole and the concentration.
All right. How would it affect the mole and concentration? Would it be higher or lower?
Higher.
Higher.
Yeah, right. So let's check again. Let us say we add the precipitating reagent in excess, and all of the chloride ions are present in the precipitate. We wash it, dry it, weigh it. If it is not dried properly, we are going to get a higher mass of precipitate than it should be. And so the concentration is going to be higher than it actually should be. If you don't see it as yet, when we do the calculation, you will see why. All right. So let us return now to this scenario. So if we have 25 mils of the water sample, after the precipitating reagent that we are using is silver nitrate. And after we have completed the process, the mass of our precipitate.
Sir,
Yes.
will they tell us the precipitate reagent that is being used?
You will have to know that it is the precipitating reagent.
No, I'm asking that if they will state it in the question.
Yes, but as in you will have to, more than one compound will be present in the question. So you will, when you see the compound, you will have to know that it is the precipitating reagent. So
Okay, thank you.
just right. So you see whatever solution is added to your sample to get the precipitate, that is your precipitating reagent. So whatever is added to the water sample, that is your precipitating reagent. So silver nitrate is added to 25 mils of the water sample that is supposed to contain chloride ions. Now the mass of the precipitate, and what would be the precipitate again? What would be the name of the precipitate? If you add silver nitrate.
Silver chloride, sir.
Right. So the mass of the precipitate, right, which is silver chloride, let us say it is 2.58 grams. That is it. So you have the water sample, you add this precipitating reagent, silver nitrate in excess, and you get your precipitate of silver chloride with 2.58 grams. And we are supposed to calculate the concentration now of chloride ions present in the sample. When you're doing the calculation, the first step we're going to do is to calculate the moles of our precipitate. So the first step, we're going to calculate the moles of our precipitate. Now, what is this formula for finding moles?
Mass over RMM.
Right. And the mass here is 2.58 grams. Silver is 108, and chlorine is 35.5. So that would give you how much?
143.5.
Right. So 2.58 divided by 143.5, how much, what is the answer?
Zero point
0.017978.
All right, so we're going to work with 0.018 and around that. Yeah. So the first thing we'll do is calculate the moles of our precipitate. It's just the mass divided by the molar mass. Can I erase the top part of the board? Is
Yes, sir.
Yes, sir.
Wait.
All right, let me know when you're finished. Okay.
Okay, sir.
All right.
Sir, question.
Yeah.
Sir, them give you the mass, right? The
That is
2.
correct. Yes, I'm going to post this after class.
No, sir, I'm saying, if they were the one that gave you the mass, sir.
Yes, they will give you the mass.
Okay, all right.
Yes. I was replying to a text.
All right.
Yeah. So after you get the mole of the precipitate, we are going to write a balanced equation for the precipitation reaction. So the second step, we know that the silver ions, right, would have combined with the chloride ions to form a precipitate of silver chloride. The reason why we are doing the balance equation, the person that is texting, I'm going to post it to YouTube after class. All right, so the reason why we need the balance equation, right? We know the moles of our precipitate, which is silver chloride. So we can use mole ratio. So the mole ratio between the precipitate and the chloride ions. We are going to use that ratio to get the moles of chloride ions. So based on this equation, first of all, is the equation balanced?
Yes, sir.
Right.
Yes,
So
sir.
what is the mole ratio?
1 to 1.
1 to 1.
1 to 1.
So 1 mole of chloride ion to 1 mole of silver chloride. So if the mole ratio is 1 to 1, this right now.
Then the same amount would have
They have
reacted.
the same mole.
Right, so the third step, so mole ratio is 1 to 1. Right, so therefore, the mole of chloride ion is equal to 0.018 mole. Now, if you want the molar concentration, what is the formula for molar concentration? Anybody remember? That is equal to mole divided
The mole
by,
over volume?
right, and the mole is 0.018. The volume must be in dm cube. So 25 cm cube to dm cube is how much?
0.025.
That is correct. Right, and you go like that.
Sir, good afternoon. Which topic is this? I just came in.
Gravimetric analysis.
Sir, it's 0.72.
All right. All right, so that is your answer. All right, now I'm going to give you a past paper question to do.
Sir, what time are you planning to finish?
Well, 48, because we're doing Gravimetric Titration and what's that again?
Uncertain.
Right, uncertainty. Tomorrow is module 2, sorry. Tomorrow is module 1 and Sunday is module 3.
Is it the same link? And what time do you usually begin?
Tomorrow, it's the same link for tomorrow. I'm not sure about Sunday. I will let you know if it's the same link for Sunday. But it will be the same link for tomorrow's class at the same time. All right, is anybody still writing from the board? All right, no answer, that means everybody has it. All right, so in step 3, when we got the moles of the chloride ions, and then in step 4, we found the molar concentration. This was because the sample was in a liquid, so we have a volume, so we find concentration. But if it was like we are trying to find the percentage of calcium carbonate in a sample of limestone, when you get the moles, so for step 4, instead of finding molar concentration, you will be finding mass instead. So in step 3, where you get the mole of chloride ion, if they want the percentage of it in the sample, you will not be calculating molar concentration, right? So tell me the mole of chloride ions again.
0.018.
0.018.
All right, 0.018. So if we're finding percentage, right? Percentage is the mass of the compound, right? Or ion divided by mass of sample. So it's the mass of the compound divided by the mass of the sample times 100. So mass is equal to, what is the formula for mass?
Mole times RMM.
Right. So it would be 0.018 times 35.5. How much you get?
0.64. 0.64.
All right. So let us say the mass of this sample was 2 grams. So it will be percentage is equal to 0.64 divided by 2 times 100. What's your answer?
32, sir.
All right, so we'll get 32%. All right, so the question, it can ask, so for this form of gravimetry, you can be asked to find the molar concentration, or you can be asked to find the percentage. It will be posted to the YouTube channel. Someone with the channel just post the link. Right, so if they ask you to find the percentage, you will first have to find the mass of the compound first. In this case, you have the moles of the chloride ion, you multiply it by the molar mass, so you get the mass of the chloride ion. The question would have given you a mass of this sample. Let us say the mass of the sample was 2 grams. It would be the mass of the chloride ion divided by the mass of the sample times 100. All right, is that clear?
Mm-hmm. Yes, sir.
All right, so now we're ready to do the question. All right, so there's a sample of impure.
What's the year, sir? Sir, what year is this taken from?
Sir, 2018, I have a very good question.
Right, this is 2018.
Oh, God.
As I'm writing this question, right? Because you never know what they may ask on the paper. So it says a sample of impure potassium chloride was dissolved in water. If we were using calcium carbonate, if we were analyzing a sample with calcium carbonate, would we be able to use water? Anybody?
No, sir.
Can you tell us why?
Calcium carbonate is insoluble.
That is correct. So what, in place of water, what would you have used? What do you know that calcium carbonate would be soluble in?
An acid, sir.
Ethanol.
Or let's say, what would the calcium carbonate react with then? Give me a substance.
Sir,
Typical
hydrochloric acid.
hydrochloric. That is correct. Right. So if the salt, so when we dissolve things in water, it's because it is soluble. So if it was calcium carbonate, we wouldn't be using water. We would have to be using an acid because the calcium carbonate would react with the acid. All right. But as the person had said, it is insoluble in water, so we couldn't use it. Because remember, you know, when you dissolve KCl in water, all of the ions will break up and be present. But if it is insoluble, it's just a slight, just a few amount would actually dissolve. So we couldn't use water. All right. So I was just pointing that out. All right. So was dissolved in water. Why are they treating it with excess silver nitrate?
To ensure that all the potassium chloride react with the silver. Ensure all the chloride react with the silver.
That is correct.
Sir, when will this be posted on YouTube?
20 minutes after class is completed. 20 to 30 minutes, yeah. Hold on, God. I think the storage is finishing up. Let's open up. As in the Zoom, you have a certain amount. Hopefully this is same. Or else they won't be recording to post. We're in a group meeting? We're in a group meeting?
Yes. In the class.
Your mic is on. The person that is talking, your mic is on.
Somebody mic is on because I'm not seeing the screen.
You're not seeing the screen?
I'm seeing it now, sir.
All right. Let me know when you're finished with the first part of the question. Or is anybody writing the first part of the question?
Yes, sir.
All right, let me know when you're finished.
All right, finish, sir.
All right.
Sir, can you hold on to?
All right, let me read. Did you have this part that I just erased?
Yes, sir.
All right, let me know when you're finished up to obtain.
Sir?
Yes.
Sir, what was the cost of the impure KCl that you remove, please? If you can just say that part.
0.45 gram.
Thank you.
Yeah. I'm going to erase the first part. Is anybody writing it out?
Breakfast and farmer, and of course.
Please close your mic. I'm not seeing the screen.
You're going to have to pin, sir.
Oh, my God. Oh, all right. The first one.
I was trying to do that.
So that is the question. I'm going to give you, I guess, 4 minutes or so, and to try it.
Sir,
Yes,
are we supposed to tell you like our answers?
you can tell me how much I get in the meantime.
For each one?
No, just tell me the percentage.
I got 97.8%.
97.8.
Yes, sir.
Give me a second and I will tell you if it's correct.
Okay, sir.
Yeah. Yes, it's correct. I got 97, but it's based on how much decimal places. But yeah.
Sir, I got 97.3.
Yeah, man. So it's 97, but based on how much decimal places I use, it might be decimal place, it can vary a little. Right? So 97% is good. But let us get that as a little more time and then work. Right, did anybody else get a different answer or the same answer?
Answer, sir.
Same answer.
All right, good. Just give me a second. All right, so calculate the number of moles of silver chloride. How many moles did you get?
0.0059.
Yes, sir, that's the same method.
Right. No.
I just rounded up to the 6.
Sir, I rounded up to 6.
All right, no problem. Hold on. If it's 0.00, all right, we're not doing the moles calculations. Yeah. All right, so 0.006, because there's 2 0 here, don't just use the 6. It's best to use at least, it will use at least 0.0059. All right? Don't go too much. All right?
Sir, can work that out, please.
Yeah, man, I'm going to pause. All right. So the first step is to calculate the moles of the silver chloride. And we know that mole is equal to mass divided by molar mass. The mass given was how much again? 0.8402 divided by 143.5, right? 0.00586. Right? So that is the mole of the precipitate, which is silver chloride. Now, the next question was to deduce the number of moles of KCl. Even though they said deduce the moles of KCl, before this question, they could have asked you a next question. What could be the next question they would have asked before asking you to deduce the number of moles of KCl? What could have been
Number of moles in Cl?
Please repeat.
The number of moles in the chloride?
All right, to get this moles, right, what did you have to do?
Balance equation.
That is correct. So we could have asked you for the balance equation, because without the equation, you could not be able to calculate the number of
I'm
moles.
hearing 2 people talk same time.
Sir, they gave you the mass, so you could have calculated the moles still without the equation.
They gave you the mass of what?
The Cl, the KCl.
You mean the 0.45 gram?
Yeah.
But it says impure, right? Impure, that means it's not just KCl present.
Okay.
Yeah, so we're actually trying to find the mass of the, so we're trying to find the pure, the amount of just KCl, so pure KCl, all right? So the number of moles of KCl to do that, and if you remember the 4 steps, after you calculate the moles of the precipitate, then we would go to the balance equation. Now, for this question, we are not interested in the chloride ion. We are interested in the entire potassium chloride. So it would be potassium chloride reacting with the silver nitrate. And what would be the product?
Silver chloride, potassium nitrate.
All right, so silver chloride plus potassium nitrate. What would be the state symbols here? For KCl, it would be
Aqueous, sir.
Yes, sir.
for silver nitrate solution. Once it's a solution, it should be what?
Aqueous.
The silver chloride, it should be what? Right, because it's a precipitate. And this is aqueous. All right. So what's the mole ratio between silver chloride and potassium chloride?
1:1.
Right. So since it is a 1-to-1 mole ratio, so since it is a 1-to-1 mole ratio, the mole of KCl is equal to what?
0.0059 mole.
All right. And so once you have the mass, once you have the number of moles of KCl, again, they skipped a step. Which step did they skip in asking you to calculate the percentage? So before asking you to calculate it,
The mass.
exactly right. So they could have asked you for the mass. Also, they didn't have to ask you any of this. The only question could have been calculate the percentage of KCl present in this sample and 6 marks. All right. So by asking, somebody's mic is on, mute your mic. Right. They could have just asked you to calculate the percentage, and you would have to remember all of the steps. So they are actually helping you by telling you along the way what to calculate. Right? So to calculate the percentage of KCl in the sample, we first need to find the mass of KCl. Again, how do we find mass?
Most time molar mass.
Most time RMA.
So mass is mole. Right. And the moles are at 0.0059, and the molar mass is
74.5.
74.5. All right, and I got this
0.44 grams.
0.44.
44 grams. Yes, sir.
All right.
Gram.
So that is the mass of KCl in the sample. So what was the mass of the sample? The mass of the sample was
It was originally 0.45.
0.450.
Right. But the actual amount of KCl is 0.44. So to get the percentage now, so the percentage of KCl is equal to the mass of the KCl divided by the mass of the sample times 100. If you use 0.44, how much I get?
I got 97.8.
All right. When I use 0.436, I got 90. How much did I get? 97 point what? Don't remember.
3, sir.
3? All right.
Or 97, sir. 97 is your answer.
Oh, okay. So as I said, 97 is good. The decimal place, it just depends on how much decimal place that you use up here. But you should get 97. All right. Now, the other part of, so here under each topic, we have like uses and so forth. But I want to get through all of the calculations in each topic first. And then if the time doesn't remain today, tomorrow we'll look at the uses and procedures. All right, for each, for gravimetry uncertainty, because you have to know to calibrate the pipette and so the procedure for all of that. But I'm going through the calculations first. If we have time, we'll look at it. If not, we'll do it the first part of tomorrow's class. All right, so for gravimetry, these are the two forms of calculations. All right, so next we'll move on to titration. All right, so for titration, we have acid base, redox, thermometric, and we have back titration that we're going to look at. For redox titration, or inert titration, right? Typically, so we used to acid base reactions, right? And in a titration, we are looking for when the acid and the base have neutralized each other. To figure it out, we are going to use an indicator. So the indicator is going to change color to let us know when the acid and the base have neutralized each other. But there are other forms of titration in which we don't have to use an indicator. So for redox titration, that is a type of titration in which we don't need to use an indicator, because for redox reactions, they will change oxidation state. And when they change oxidation state, you will get a color change. Now, in terms of calculations, redox titration, acid-base titration, thermometric titration, there's no difference in the calculations. The only difference is how do we know when neutralization has occurred. For acid-base, the indicator is going to change color. For redox, the reagents will change color. And for thermometric titration, we are using temperature readings. So for thermometric titration, what we would have done right? You would have their conical stars, right? Thermometric titration. So you would have your conical flask, right? Let us say the acid is inside of it. It's here. You will have your burette. And remember, acid base in terms of energetics, if you remember that, acid base reactions are what type? Exo or endo?
Exothermic.
Right. So heat is going to be generated. So let us say the base is in the burette. So we would add specific amounts of base to the acid. So let us say in 5 cm³ increments. So we measure the temperature of the acid first. So at 0, when you don't add any base, so we start out with 0 cm³, right? When you don't add any acid. And let's say you measure the temperature of this solution and it's 26. Then you add 5 cm³ and you record the temperature. Let's say you get 27. You add 5 more cm³, right? Let's say the temperature goes up to 28. You add 5 more cm³ again. Let's say it goes to 29.5. You add 5 more cm³, it goes to 30. You add 5 more cm³, it stays at 30. You add 5 more cm³, it gets at 29, and it starts to decrease. With thermometric titration, and in each titration, something must tell us when the acid and base have neutralized each other. For thermometric titration, we are using temperature readings. The highest temperature reading that is recorded, that is what indicates neutralization has occurred. So in terms of calculation, nothing is going to change because all we want to know is what volume was used for neutralization. That's it. The same thing with our regular acid base. We just want to know the volume used for neutralization. It is just the technique for obtaining the volume that is used for neutralization. So the calculations are not going to change. You still calculate the moles at your base, write your balance equation, mole ratio, get the moles of the unknown, and then find the concentration. So the calculations are going to stay the same. Each technique is different for obtaining the volume used for neutralization. All right? But tomorrow's class, what time? No? To do back titration, and that probably take a little time. So yeah. All right. So We're going to focus on some calculations now, but before I give you any past paper, we're going to practice one on the board, right? So we're going to practice 2 questions, then you get the past paper. Sure. Can you see the paper or the tool?
It's okay, sir.
Can see, sir.
All right. All right, so if we go on the exam, right, and you get a titration table, when you get the readings, so the volume used, remember it's initial from the final, give you the volume used. Now, if you would be asked, or you have to know that we must calculate the average volume used. Now, if you look, we have 3 values. First of all, can we average all 3 of these?
No,
No, you
sir.
have to average the two
The one that
closest.
are closer
Two
together.
closest.
Yeah, 2 closest.
Exactly. All right. Let us say this was 27.4. Would we average the 3 of them now?
Yes, sir.
Yes, sir.
Yes.
Yeah.
All right. So it's when the numbers are a little off. So you always average the 2 closest, assuming that only 2 of them are extremely close. You average those 2. Right? What was here? 25. But if the 3 of them are extremely close, then you average the 3 of them. So this example, it says table showing the volume of HCl used. So you can just write off this quickly, right? And we're going to do the calculation. So this is the volume of HCl.
Finished, sir.
All right.
Sir, I'm not seeing your screen.
I'm not sure why not seeing it. Probably can just exit and come back. I'm not sure.
No, I'm seeing it now.
All right. Right, so as soon as you are finished writing, we will work it together. And of course, the table here is the one you just drew. Is anybody still writing?
No, sir.
No, sir.
No, sir.
All right, so when you get a titration question, I want you to just read through it and pick out all of the information. So anyway, see a number, just highlight it. So let's go. So it says, in order to determine the molar concentration of a sodium hydroxide solution, an acid-base titration was conducted using a 0.15 moles per dm cube solution. It should be solution, it should be HCl solution. Right? So using a 0.15 moles per dm cube hydrochloric acid solution. So moles per dm cube, that is the unit for what?
Concentration.
Right. So at this point, they gave us the concentration of the hydrochloric acid solution. So let us make a note of that. So for the hydrochloric acid solution, we have the concentration, which is 0.15 moles per dm cube. Now it says a 25 ml pipette was used to deliver the sodium hydroxide solution into the conical flask. What is this sentence telling us?
The volume.
The volume of what?
Sodium hydroxide.
Right. Because if you are using a 25 ml pipette, what volume are you using?
25 cm.
Right.
25 cm cube.
That is correct. So the volume is here. I remember cm cube and mil, it's the same thing. So they gave us at this point, we have the volume of sodium hydroxide. Then it says the table below shows the results of 3 trials. Use the data to calculate the molar and mass concentration of the sodium hydroxide solution. So they want us to calculate both forms of concentration for this sodium hydroxide solution. Now, in any titration, you have to be given the volume and concentration for one of these substances. All right, you must be given concentration and volume. So you will look in your question, whichever substance you get concentration and volume for, you are going to use that and calculate the number of moles. The other substance or the other solution, you will only be given the volume and be asked to find the concentration. It doesn't matter what the titration is, because the purpose of titration is to find the concentration of a solution. And to do that, you have to have a standard solution as well. And the standard solution, as we know, is a solution whose concentration is known. So in every titration, you will get concentration and volume for one of the solutions. And the next solution, you will only get the volume and you will have to work on the concentration. So concentration, volume, volume. But the table, what was in the table?
The result.
For which substance?
Hydrochloric acid.
HCl,
sir.
Right. So the first thing that we would do, since as we were given the volume of HCl, but it was
Find the moles for HCl.
Going to find the average volume.
Right. So because it was a set of volumes, we have to calculate.
Oh, yeah, 27.1 and 27.3.
volume of HCl. Then just tell them about the numbers.
27.1 and 27.2.
27.1 and 27.2 divided by 2. How much you get?
So you're gonna get
27.15.
27.2, sir. 1.5 or 27.2.
No, don't round off.
27.15.
27.15, sir.
All right. Right, so 27.15 cm3. So now we have the concentration of the hydrochloric acid and we have the
Volume.
So just remember, whichever solution I have concentration and volume for, what are you going to do?
N equals C over V.
All right, you are going to find the number of moles.
Yes.
So remember, if concentration is equal to mole over volume, what is the formula for moles?
Sir, I said N equals C over V.
N equal C.
C over V.
And N is what?
Moles.
No. And C is concentration?
Yes, sir.
No. It would be C.
Multiplication.
No, if I use N for moles, if I use N for moles, then concentration is N over V. All right, look here. Let's say you went on the exam, right? And you write N is equal to C over V. Concentration is moles per
divided by
dm cube, right?
Yes.
Divided by 1.
Yeah.
Divided by 1 over dm cube, right?
Yes, sir.
Let's see if the units work out. Mole per dm cube divided by 1 over dm cube.
dm cube, go cancel dm cube, sir. You go left back with more.
I'm going to left back with mole. But I'm supposed to multiply. Mole is concentration times the volume. All right, let us see all quickly. The mole per dm cube times volume, which is dm cube over 1. So end with mole. Let me go again. So you add concentration over volume. Then you flip it. I should flip it. No, anyways, no, but it's multiply supposed to multiply them.
Yes,
not,
sir.
Not divide.
The volume will be at the bottom.
Please repeat.
The 2 volume will be at the bottom, will be mole over dm cube times dm cube. Because the volume at the bottom, innit?
It's actually concentration that's equal to moles divided by
The
volume.
concentration equal mole over volume, right?
Yeah, man. Yeah.
And remember, for the volume of the BF2, so basically divide by dm cube. So that means mole over dm cube multiplied by 1 over dm cube.
So it will work out to mole over dm cube times the 1 over dm cube. So
Yeah.
they wouldn't be able to. So they wouldn't be able to cancel. All right. No.
Sir, times concentration. Volume.
Yeah. No, man. No, it's repeat. Go ahead.
So I'm just saying this times concentration times volume.
No, just use the formula. Use the formula. Concentration equal mole over volume. So that means the concentration will equal to mole divided by volume.
Yeah, man. What I was
I'm talking about moles.
If you're in the exam and you write the formula incorrectly, the units should let you know if the formula is incorrect. Because if the units don't match up, then your working out is incorrect. So like this year, you wouldn't be able to get mole alone as the unit. So I was just letting you know that as well. So if you forget the formula, or you want to be sure that your formula is correct, work out the units. And your units will let you know if it is correct. All right, so mole is concentration.
So you can also use a triangle.
Yeah, man. Anyway, so there's no one set way for working moles. But if you're whatever you're okay with. But for step 2, just find the moles. All right. So however you know how to work it, you work it. All right. So the mole here, it would have been the concentration, which is 0.15 moles per bm cube times the volume in bm cube. I know some of you might divide by the 1000 cm cube, but when I'm teaching, I just convert the volume to dm cube. So 27.15 cm cube to bm cube, it would be 0.02715 bm cube. Remember, from cm cube to dm cube, you divide by 1000. Right, so bm cube cancels bm cube. We're left with moles. All right, so 0.15 times 0.02715. 0.00407 moles. All right. So you find the average volume, you calculate the moles. What should we do after we get the moles of HCl? Remember, our objective is to get the concentration of sodium hydroxide. To get the concentration, we need the moles because we already have the volume. So all we need is the mole of NaOH. That is correct, Tisha. All right, we need the equation. So when sodium hydroxide reacts with HCl, what is going to be produced?
Sodium chloride and water.
Sodium chloride and H2O, yeah.
Right, that is correct. Remember to put in your state symbols, all right, all of them. What is the mole ratio between sodium hydroxide and HCl?
1:1.
1:1.
1:1. Step 4, since the mole ratio is 1:1, the mole of NaOH is equal to 0.00. Moles. All right. So once we have the moles of sodium hydroxide, what can we calculate next?
The concentration by using the volume.
Right, that is correct.
Yep.
So you can read out the number that you have for mole for NaOH because it's kind of grainy.
0.00407. 0.0. Good?
Thank you.
All right. What was the volume for the NaOH again? 25.
Yes.
That will be 0.0.
0.025 bm cube.
That is correct.
Zero point 0.16.
0.16 moles per dm cube. Now, we know that mass concentration is mass over volume. However,
Concentration times RMM.
that is correct. When you're doing a titration, if you calculate the molar concentration to get the mass concentration, you will simply multiply the molar concentration by the molar mass of the compound. In this case, that is sodium hydroxide. So step 6, the mass concentration is equal to molar concentration times the molar mass. I want to say RMM. So it's 0.16. And let me show you that the units work out. So moles per dm cube and the molar mass for sodium hydroxide is 40 grams per mole. So mole cancels mole, you're left with grams per dm cube. It's 6.4 grams, 6.4 grams per dm cube. All right. So let me give a question now, actual past paper, and then we look at back titration. Let me know as soon as you're finished, you let me know.
I'm finished.
Is anybody else still writing?
No, finished, sir.
So remember, with acid-base titration, redox titration, thermometric titration, the calculations are still the same. It's just the procedure that is different. So I'm going to put a redox question on the board, but as I said, the calculations still the same, just the procedure. And the procedure is the same as well. It's just that you don't need an indicator. That's it.
Sir, we share.
This one is an old one. I'm going to put my email address on the board shortly. And after class, you can email me and I send it to you. But this one is an old paper. I don't remember exactly which year. Probably 2000, early 2000. Right. When you're finished writing it up, I will put the actual questions. And is anybody writing still?
Yes, sir, I'm writing. I'm at
Alright.
the equation for the.
No problem. So,
Sir, is that 8 hydrogen?
yes, that is correct. 8 hydrogen.
Sorry, I forgot decay in potassium permanganate in the reaction side.
Hmm?
Is that potassium permanganate supposed to be in the reaction side?
Here? This?
Yes, sir.
It's a redox reaction. The potassium ion, it doesn't take part. That part is broken off.
Okay.
So, right, so it's K plus and the MnO4 minus. Right. And it's this that takes part. All right, so you can try that. The mass of iron is 56. Any answers, Azet? Any answers? All right, so we should all be able to at least be able to work out the number of moles of KMnO4. Did we do that?
Sir, I got 0.00496 more.
0 point, let me see. Right, I got that as well. All right, so let me erase this part. So as I said, in every titration, you will get concentration and volume for one of the solutions. Whichever solution that is, you work out the number of moles. In this case, it's KMnO4. So mole is equal to concentration times volume. And the concentration was, what was the concentration?
There was 0.02.
0.02 moles.
All right. Times it by the volume, which was
24.80, which is 0.02480.
0.022.
24, sir. 0.02480.
All right.
Yeah.
Yes, and I got the 0.004. Right. So that's the mole of KMnO4. And next, they wanted us to find so after we get the moles of KMnO4, we were to find the number of moles of Fe2 plus in 25 cm cube. How did we do that? Anybody?
We use the mole
So did
ratio.
Sir, use the mole ratio, sir. It was a 5-to-1.
That is correct. Mole ratio, right? So let's use the mole ratio. Now, what is the mole ratio? So for iron, it's 5 moles of iron to 1 mole of KMnO4.
KMnO4, 5-to-1.
No, even though it's 5-to-1, you have to be careful how you read it, right?
Yes, sir.
So the mole ratio is 5-to-1, but which one of them do you have the moles for?
So we have
MnO4.
MnO4. Potassium.
So how are we going to get the moles of iron?
Divided by the
We're going to
Multiply,
we're going to
sir.
cross multiply, sir.
Sir, multiply by 5.
Right, because so even though it's
Yeah.
5-to-1, we know the moles of KMnO4. That means we want to know the moles of iron. So you have to multiply. We know the moles of the permanganate, and you want the moles of iron. So it's 1, it's going from 1 to 5. So even though in the equation it's 5-to-1, you have to look at the fact that we have the moles for KMnO4. So it's 1 to 5. Understand?
Sir.
Right. And if I want to remember, when it comes to mole ratio, just for mole ratio, if you going from smaller number to a larger one, you multiply. And from the larger one to the smaller one, you divide. So to get the moles of iron, we're going to divide by
Multiply, sir.
multiply by 5. So
Sir,
it's
I
going
got
to be 0.00496 times 5.
Sir,
Yes?
2.48 times 10 to
question.
the
Sir, I got 0.
Sorry. 0.0.
0.0248.
Right. The person with the question, go ahead.
Sir, the 0.00496, isn't that the volume for 24.8? We're trying to find the volume for 25.
Well, no one. So the first question asks us to find the moles of KMnO4. So this is the volume of KMnO4. in dm cube, and we times volume by the concentration, that gives us the moles. All right? So volume times concentration gives us the mole of K, MnO4. To get the moles of iron in 25 cm cube, remember it was 25 cm cube that was used in the titration. So this amount of moles of KMnO4 reacted with the amount of moles of Fe2 plus that was in the 25 cm cube. So whatever amount of moles of iron that was in the 25 cm cube, it reacted with 0.00496 moles of KMnO4. That is why we can use the mole ratio to determine the number of moles of Fe2 plus in the 25 cm cube. Is that any clearer?
Yes, sir.
All right. So we times it by 5 and we get the number of moles of Fe2 plus in the 25 cm cube. Now, after we get the moles in 25 cm cube, where's my eraser? After we get the moles in 25 cm cube, they ask us to find the number of moles in what? Volume.
1 dm cube.
All right. So you can convert the 25 cm cube to dm cube, or convert the 1 dm cube to 1,000 cm cube. So what we're going to say, right? This amount of moles, so 0.00248 moles is in 25 cm cube, and we would like to know how many would be in 1,000 cm cube. Remember, 1 dm cube is 1,000 cm cube. And so we'll just cross multiply, and we'll get x is equal to 0.00248 times 1,000 divided by
0.099.
0.099.
Yeah, more.
All right. So this is the amount of moles in 1 dm cube, or 1,000 cm cube. So once you know how much was in the 25, it's just a simple relation between the 25 and the 1,000 to get the amount of moles. So this part is, so this was which part of the question? So it was part 1, then this was part 2, and this is part 3. All right. And then part 4, it asks us to calculate the mass in 1 dm cube.
Yes, sir.
All right. So this mole here was for 25 cm cube. This mole was for the 1 dm cube. What is the formula for finding mass? Mass is equal to?
More times molar mass.
Right. I'm going to erase number 1. Does everybody have it already?
Yes, sir.
All right. Right, so for part 4, mass is equal to mole times molar mass. All right, so it's 0.099 moles times that's 56 grams per mole. What was the answer again?
5.56.
5.56 grams. All right, so this mass is in 1 dm cube, right? So we have 5.56 grams in 1 dm cube. If we have 5.56 grams in 1 dm cube, what is the mass concentration?
5.56 gram per dm cube.
All right. This is not part of the question, but I'm doing it for a reason. All right. Now, what is the last part of the question? What does it ask us to do?
So we're supposed to calculate the percentage.
Right. Calculate the percentage mass of Fe2 plus in the solution of M. And what was given in bracket?
The mass concentration of M is equal to 40.
So remember, percentage will be equal to what? The mass of iron over the mass of this sample, right? So what is the mass of this sample?
So 40.90 that they gave us.
Tell me why you said 40.96.
90, sir.
Yeah.
Sir, but,
Tell me why you use that.
sir, because it's the mass of M. Oh.
M is the solution.
Yeah, also, that is the mass you are supposed to use.
So it is a compound, sir. M is the compound.
In one dm cube. So the mass of iron here, right? This mass, it's the mass of Fe2 plus in one dm cube. So you have 5.56 gram in one dm cube. So what the reason why I write 5.56 gram per dm cube, I'm just letting you know that they gave us, writing it like 5.56 gram per dm cube is telling us the mass that is present in one dm cube. So when they say that the mass concentration of M is 40 grams per dm cube, don't really pay attention to the dm cube. They are telling us that we have 40.90 grams in one dm cube. All right. So in one dm cube, we have 5.56 gram of Fe2 plus and 40.90 gram of M. So what should we divide?
Sir, the 5.56 or
over the
5.56.
40.90.
That is correct. So even though it's the mass concentration, but the mass concentration is telling you the amount of mass that is present in one dm cube. So you just take out the mass and use it. Right. And what, so it is
0.136.
Times 100. How much again?
13.59.
All right. So 13.59%.
Yeah.
All right. No, that is where the question has stopped.
Sure.
But yes.
Sir, somebody asking you to repeat.
Which part? The last part? All right, let me just repeat the last part. So
I was asking about the part before the percentage where you were talking about the 40 over the 1 dm cube.
right. So yeah. So the question had asked us to calculate the percentage of iron. So to get the percentage, it's the mass of the iron Fe2 plus over the mass of the sample. But they did not give us the mass of the sample M. They gave us the mass concentration, which is 40.90 grams per dm cube. So what I was saying, right, is that even though they did not say 40.9 grams, the solution that we're dealing with is one dm cube. So we have calculated the mass of Fe2 plus in one dm cube. So 5.56 gram of Fe2 plus is in one dm cube. So we know that. So when they tell you that the mass concentration of solution M is 40.9 grams per dm cube, they are telling you that in one dm cube, you have 40.9 grams of M. Right? So we have just separated the mass from the volume. So this is how we know that we have 40.9 grams of M. So in 1 dm cube, we have 5.56 grams of Fe2 plus and 40.9 grams of M. And so we can divide the mass of Fe2 plus by the mass of sample M, which is 40.9. Understand?
Yes, sir. Thank you.
All right. Let me check about something. All right, so we have to do back titration as well. I know it's 8:30, but I'm going to do it. All right, in part 2, right, where they ask for the number of moles of Fe2 plus in 25 cm cube, for part 3, they could have asked us to calculate the molar concentration. So after step 2, where they say the number of moles of Fe2 plus in 25 cm cube, or even after step 3, where they say the number of moles in 1 dm cube, they could have asked for the molar concentration. So at that point, we would have done what? So if after step 2, we calculate the number of moles of Fe2 plus in 25 cm cube, if they had asked us to calculate the molar concentration, how would we have done that?
Sir, would it be the concentration times the volume?
The 25 cm cube, sir.
Repeat.
Would you have used the 25 cm cube?
Yes, that is correct. And what else?
And the concentration?
No, we are finding the card. Let's write it on the board. So after you do step 2, right? After you do step 2, answer this question. So this is my part 3. So calculate the molar concentration of Fe2 plus. So after the step 2, which was to find the number of moles of Fe2 plus in 25 cm cube of solution M, I wanted to calculate the molar concentration of Fe2 plus in the 25 cm cube. So how would we have done that? All right, so molar concentration, what is the formula?
Sir, wouldn't we use this the 0.0024 moles that we found?
Yeah. We would use the 0. That is correct. So we would use the 0.00248.
48, yeah.
How much
Divide
zero?
by 2 0, sir.
Right.
I divided by the 25, 0.025.
VMQ, right?
Yeah.
So the question, it could have gone in this direction as well. And what would have been our answer?
0.0992.
0.0992?
Yes, sir.
Moles per VMQ. And if we have then now been asked to find the mass concentration, how would we have done that? In the same 25 cm.
Sir, you use the
the answer that we got, sir.
The
That is correct. Right. So the molar concentration times
the mm.
Right. So it's 0.992, no, 0.092 moles per VMQ times 56 grams per mole. Mole cancel mole. What is our answer?
5.556.
5.556. 5.56.
Yeah.
Hold on. When I realize this, what do I realize here?
It is same as the Fe.
You realize, yes, it's the same thing we got, right? The 0.56 per mole.
In 1 dm.
The mass of Fe2 plus in the 1 dm cube, how much was that? 5.56, right?
Yes, sir.
Exactly. Yeah, so it could have come in this format as well. All right. All right, so as soon as I finish writing, you let me know, and we'll go to back titration. Anybody
Yes,
writing?
sir.
All right, good. Now, a back titration, it's also called an indirect titration. Right, now everybody understand how to do titration, right? So before I even tell you that I'm doing back titration, I'm just going to put a scenario on the board and we'll look at it. So let us say we have a container, right? And inside of the container, there are 100 mils of HCl, right? And the concentration is 0.5 moles per dm cube. Now, inside the container, you put 2 grams or you put 1.5 grams of calcium carbonate. So you put 100 mils of 0.5 moles per dm cube hydrochloric acid in a container with just 1.5 grams of calcium carbonate. Do you think all of the HCl is going to react with this small amount of calcium carbonate?
No, sir.
No, sir.
No, exactly. So let's just say the calcium carbonate, it's not your pure calcium carbonate, it's in a mix. So let's say it is limestone. So you have 1.5 gram of limestone. But we are trying to find out of this 1.5 gram, how many of it is actually limestone. So what we need to do, right, because we know that limestone, it contains calcium carbonate. So if we react calcium carbonate with hydrochloric acid, we are going to get what? If you have calcium
Calcium
carbonate
chloride, sir, and
Calcium chloride and water.
and something else.
Carbon
carbon
dioxide.
Dioxide, sir.
dioxide. Carbon dioxide.
All right. So it is kind of pretty straightforward, right? You react calcium carbonate with HCl, you get calcium chloride and CO2 and water. You balance your equation and you can just easily use mole ratio, right? To get the mole of calcium carbonate. Because what? You know the concentration of HCl and you know the volume. So if you have concentration and volume, what can you find?
The mole.
The mole, right? So we can multiply these two to get the mole of HCl. And then we just come to our equation and use mole ratio and get the mole of calcium carbonate, right?
Yes, sir.
Straightforward, right? Straightforward, good. So there shouldn't be a problem. However, you only use the mole ratio if you know that, if you are certain that this amount of moles actually reacted with the 1.5 gram. But we just agreed that this is too much acid in terms of moles, not the volume. In terms of moles, it is more than the 1.5 gram of limestone. So the question is, how are we going to know how much HCl actually react? So let me just calculate the moles of HCl. So the mole of HCl to be equal to 0.1 dm³ times 0.5 moles per dm³. How much would we get?
0.05.
0.05 or 20?
10, sir. 0.05.
All right. So the question is, how much of this moles actually react with the limestone? We don't know, right?
Sir, is it this way you use like the 1,000, like 1,000 react with this? They want to find like 0.05 more react with how much?
Yes, I think that's what we are getting to. So the point is, how do we proceed from here? We know that once we know the moles of HCl, we can use molation and find the moles of calcium carbonate. But the problem is we use too much HCl, so we don't actually know how much react with the calcium carbonate. We understand so far?
Yes,
All
sir.
right.
Yes, sir.
Good. Now, this equation is still going to stand, because this is how we are going to find the mole of calcium carbonate. Good. Now, when this reaction is completed, right? What if we found out that of the 0.05 moles of the HCl, what if we found out that only 0.02 reacted? Remember, at the start, we don't know how much of the 0.05 actually reacted. But let us say we found a way to figure out how much reacted. And we found out that 0.0 of the 0.05 moles, 0.02 reacted with the calcium carbonate. What would we then do?
Find the mole of the.
Sir, could you repeat the question?
All right. So we were stuck at the point where we know that we use 0.05 moles of the HCl, but it was too much, so we didn't know how much actually reacted. So I'm saying, what if there was a next procedure that allowed us to know how much actually reacted? So let us say we found out that 0.02 moles reacted with the calcium carbonate, actually reacted with it.
Sir, then you use the mole ratio to find the moles of calcium carbonate.
Exactly. So 1 mole of calcium carbonate reacts with 2 moles of HCl. So if you know that 0.02 moles of HCl reacted with a calcium carbonate, how would we get the mole of calcium carbonate?
Divide that by 2.
Divided by 2.
Divide it by 2. All right. So back titration now. It's basically, this is what happens. You do a reaction, right? So remember with precipitation and gravimetry, where you add your precipitating reagent in excess to ensure that all of the analyte reacted?
Yes, sir.
Going over, no, I'm going to stop at back titration. I will have to continue tomorrow. Right, so I was saying, what was I saying? I don't remember.
So you were saying that when we use the precipitation thing.
Oh, right. So we use so we add the precipitated reagent in excess to ensure that all of the analyte in this sample reacted. It's the same thing here. We want to ensure that all of the calcium carbonate in our sample reacts. So we add the hydrochloric acid in excess. So because we add it in excess, we don't actually know how much reacts. So what we do after the reaction is completed, any HCl that is unreacted, we do a titration. And remember, in a titration, we can find out the moles of the unknown substance, right?
Yes, sir.
So what we would have done is after this reaction is completed, we know that not all of the HCl is going to react. So we do a titration with whatever moles of HCl that did not react. And so, based on the balance equation in the titration, we're going to find out the number of moles of HCl that did not react. Now, if you know the total mole of HCl, and then you do a titration and found out the number that did not react, can we find out how much actually reacted?
You just subtract.
Yes, sir. Just subtract it.
Just subtract it.
0.03.
So let us say in the titration, we found out that 0.03 moles of HCl did not react. So that is what we would do. The unreacted from the total would give us the amount that reacted. Understand?
Yes, sir.
Yes, sir.
And then now, once we find out that, we come to our balance equation and we get the moles of calcium carbonate. And mole times molar mass, we get the mass. All right? So this is what happens. I am going to put this in the form of a question. We work it, then I give you your past paper to work. All right? So I'm going to put this in the form of a question and show you how to work it. Then you will get your past paper. And we will end there for tonight. And pick up again. All right, as soon as I finish writing, I will show you how to work it.
Ready when you are, sir.
All right, good. All right, so when you get the hot titration question, you're going to, well, I'm not sure how you learn it, but I'm going to separate it into two parts. The first part of your question, it's always about the reaction that is taking place. So in our example, it would be between the calcium carbonate and the hydrochloric acid. So we have a reaction that is taking place. Once that reaction is completed, the solution that was added in excess, we're going to use it in a titration. So the information for the titration is provided in the second part of the question. So the first part of the question is always the reaction. And then the second part now is the titration. So As usual, let us read the question and pick out the information. So in order to determine the percentage of calcium carbonate, a 5 gram sample, so the sample is 5 grams. The sample was added to 100 mils of 0.5 moles per dm³ HCl. So we have the volume and the concentration for the HCl. So the reaction is between the 5 gram sample and the 100 mils of 0.5 moles per dm³ HCl. So that is the reaction. Here comes the titration. The unreacted, or they may say excess HCl, was used in an acid-base titration with sodium hydroxide. The solution was neutralized by 22.50 cm³ of 0.15 moles per dm³ sodium hydroxide. Determine the percentage of calcium carbonate. We are going to write out this information, but in 2 separate columns on your page. So one side of the page, you will have the calcium carbonate and the HCl. And then the next part, you will have the information for the titration. So let us deal with the reaction first. So we know that we have a 5 gram sample. That's for sure. And then we are using HCl. And for HCl, we have the volume, which is 100 cm³. And we have the concentration, which is 0.5 moles per dm³. All right, so let us look at the reaction first. So this is the HCl and the sample, which contains calcium carbonate. But titration, just like any other titration, whatever you're given the volume and concentration for, you're going to calculate the moles. Now in the reaction, whatever moles you get, that is the total amount of moles. So the total moles of HCl, because remember, not all of it is going to react. So whatever you start out with, that's the total amount. So the total moles of HCl, this is what now, 0.5 moles per dm³ times 0.1. And we said this was 0.05 moles, all right? So you work out the total moles of HCl. We know that the HCl, it reacted with the calcium carbonate. So calcium carbonate plus HCl give you calcium chloride, carbon dioxide, and water. And we know that the mole ratio is 1 to 2. All right? This is what we do for the reaction. Calculate the moles of your HCl, set up your balance equation. All we need to get the mole of HCl is the number of moles of HCl that actually reacted. But to figure that out, we have to go to the titration. Now in the titration, we have used sodium hydroxide. Just remind me of the concentration. Remind me of the concentration and the volume of NaOH. What was the volume I gave you?
25, sir.
25, all right.
And the concentration was 0.15.
0.15. All right. So again, they are given concentration and volume, work out the moles. So the mole of NaOH is equal to concentration, which is 0.15 times the volume, 0.025. What's your answer?
Sir.
0.7 times 10 to the minus 3.
0.0375.
All right, yes, same thing. 0.003 75 moles. All right. So this is the mole of sodium hydroxide. Remember, what we are trying to find out is the number of moles of HCl that is used in the titration. So to do that, we need an equation between sodium hydroxide and HCl. And we know that the mole ratio between NaOH and sodium chloride is 1:1. So the unreacted HCl is equal to 0.00375 moles. So if the unreacted is 0.00375, and we know the total mole from the reaction is 0.05, how would we calculate the amount that reacted?
So we're going to subtract it.
Right. So the reacted is equal to total.
Sir, for the volume for sodium hydroxide, wasn't it 22.5?
It was 22.5? No, I was asking what someone had said 25.
Yes, sir. Sorry, my bad. Yeah, it was 22.5.
All right, let's just keep it at 25 since I had worked it out already. All right, so let's switch it to 25. All right, so we are here now. So the reacted, it was the total minus the unreacted. And that would be equal to 0.05 minus 0.00375. And we get 0.046. 0.046. All right. So let us just pause here and run back through quickly. We separate the question into one portion for the reaction and the next portion for the titration. In the reaction, we found out the total moles of HCl that was used, and we set up a balanced equation for the reaction and the mole ratio. We cannot do any more as yet because we don't know the actual number of moles of HCl that will react with the calcium carbonate. So now we move over to the titration to figure out that answer. So you've got the concentration on volume for the NaOH, you work out the moles, set up your balance equation between NaOH and HCl. And you found out that the unreacted mole of HCl was 0.00375. So to figure out how much actually reacted mole, it's a simple subtraction, and that is what we did. So we found out that 0.046 moles of HCl reacted with the calcium carbonate. So now we can go ahead and say that the mole of calcium carbonate is 0.046 divided by, because we're going from, we know the mole of HCl and we want the mole of calcium carbonate from 2 to 1. All right, so we divide it by 2 and we will get 0.023. All right, So the mole of calcium carbonate is 0.023.
Excuse me, sir.
Yes?
Someone in the chat was asking if the volume used for NaOH wasn't 22.5 cm cube instead of 25.
Right. Tell them we made a mistake and we're just working with the 25. All right?
Okay.
Yes. So just everybody, just change the 22.5 to 25. Right. So the mole of calcium carbonate is 0.023. So now that we know the mole of calcium carbonate, can we find the mass of calcium carbonate?
Yes, sir.
Yes, sir.
Mole times the molar mass.
That is correct. The mole times the molar mass is 0.023 times 100. And that would give us 2.3 grams, right? Good?
Yes, sir.
And so if we want the percentage now, how would we get the percentage?
Sir,
I will put 2.3 over 5
Over the 5 grams.
divided by 100.
That is correct. So I'm just going to erase up here. So the percentage of calcium carbonate, it's 2.3 divided by 5 times 100. And what's our answer?
46%, sir.
All right. Do you want the past paper or you want to wait till tomorrow? You want to work it now?
Sir, you can give us a question.
You can work yes, sir. Can you give us the question?
All right. As soon as, just let me know when you're finished with the board and I put on the new one.
I'm finished.
All right. Is anybody else writing? All right. Remember, when you react ammonium chloride and sodium hydroxide, you get salt, ammonia, and water. So this would be so that's the equation for the reaction. This is not 0.1, it's 100 cm³ of 1 moles per dm³, not 0.1. Because if you get to the other part, you will realize that it wouldn't add up. So it's 1 moles per dm³. Did anybody get an answer? I'm going to work it.
Sir.
Yeah.
So what's the molar mass for ammonium chloride?
53.5.
All right, thank you, sir.
Yes, someone said 79.980. Right, that is correct. So depending on how much decimal place. So 79 or 80, that is correct. So good job. Please repeat. So in the question, let's see which of these are. All right, so in the question, we got the 100 cm³ is 1 moles per dm³ of sodium hydroxide reacted with 5 grams of horizontal of ammonium chloride. After that reaction is completed, the excess sodium hydroxide was used in a titration with sulfuric acid, and 25 cm³ of 0.5 moles per dm³ sulfuric acid was used. So let's go ahead and work it out. Right, so for the reaction, we now use sodium hydroxide. So the total moles, it will be the 0.1 moles per dm³ times 0.1, no, what was it now? 1 moles per dm³.
0.1 dm³ times
Right.
1 mole per dm³.
And that would have given us 0.1 moles. Right? So that's the total mole of sodium hydroxide. And for the reaction, it's sodium hydroxide reacting with ammonium chloride. Someone mic is on, mute the mic. All right, so it's sodium hydroxide plus ammonium chloride, equals sodium chloride, ammonia, and water. And we know that it's either the balance and the mole ratio is 1 to 1. All right, but this is where
Sir.
we get, yes?
Sir, oh, you're right. That equation first is in H.
Right. So we're just looking at the reaction first. All right. And then now we cannot do anything further as yet because we need the actual moles of NaOH not reacted. So we come over now to the titration. And in the titration, we use sulfuric acid, right? And the moles of sulfuric acid was 0.5 times 0.025, and we got 0.0125 moles. So again, we need a balanced equation. Sodium hydroxide react with sulfuric acid, acid and base, to get salt and water. This time, it's a 2 to 1 mole ratio. All right, so 2 moles of sodium hydroxide, 1 mole of sulfuric acid. So the mole of NaOH is equal to 0.0125. 1 mole of sulfuric acid to produce 2 moles of this, R2, react with 2 moles. So we multiply it by 2, and we would get 0.025. No, so this is the unreacted moles of NaOH. So this is the unreacted mole of NaOH. What was the volume of NaOH? Sorry, the volume was 25 cm3. No, hold on. So remember, it's 2 things. We use 100 cm3 in the reaction. Not 25, sorry, just 100 cm3, but we convert it to cm3 here. So 100 cm3 is 0.1 dm3. I will reply to someone in the chat. You can,
Sir, I have a question.
Yes.
If you have 2 NaOH plus
Yes.
the H2SO4, it's a 2 to 1 ratio. So that means you have 2 NaOH and 1 H2SO4. So why we multiply and not divide?
All right. The ratio says 2 to 1, right?
Yes.
But we know the mole of sulfuric acid, and we want the mole of this. So it's 1 mole reacting with 2 moles. So you have to look which one you have.
Okay.
2 to 1, we actually have, we know the mole of this one. So you get from 1 to 2, so you times it by 2.
All right, that's fine. Yes, sir.
So once you have the go ahead.
Yes, sir. Question with that, sir. The equation, sir. We see you have NaOH react with H2SO4. We see you have NaCl as a
Thank you very much. As it's supposed to be sodium sulfate.
Yeah, Na2SO4.
Thank you for that. All right. So we have the total mole of HCl from in the reaction, and we have the unreacted mole here. So how would we get the number of moles that actually reacted?
Subtracting.
Right, subtract. So reacted mole is equal to total minus unreacted. And that would be equal to 0.1 minus 0.025, and you're supposed to get 0.075 moles. All right? So 0.075 moles of sodium hydroxide reacted with ammonium chloride. So come back now to the reaction. If the mole ratio is 1:1 and the mole of NaOH that was used is 0.075, then the mole of ammonium chloride is now equal to what? How much would you get for the mole of ammonium chloride?
The same 0.075.
0.075.
Right, 0.075 moles. And once you have the moles, you can go ahead and get the mass, which is
Mass.
equal to
Mole times molar mass.
right? So that is 0.075 times 53.5. And we should get, how much did I get? 4 grams? All right, 4 grams.
Yes, sir.
All right. And now the percentage is the mass of the compound, which is the 4 grams, divided by the mass of the sample, which is 5 grams, multiplied by 100. So 4 divided by 5 times 100, we should get 80%.
Yes, sir.
But if you use decimals, it changes slightly. All right. If you use 4 point something, it will change slightly. All right. Or if you round it off to 4, you will get 80. Right. So that is what I'm saying. If you use the decimals, it will change a little. But if you round it off to 4, you will get 80 exactly. But it doesn't matter because it won't change a lot, just a small amount. Right? So if you did it and get it correct, good job. Any question? All right, so let me just stop the recording here. One second.